So I want to build a reverse delay that works on a live audio input. So I want it to write into a buffer continuously. So it'll wrap around the buffer, writing continuously, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds, something like that, depending on how long of a reverse delay I want to be able to achieve. And the max length will be 50% the size of the buffer, so as to avoid hitting the part of the buffer that's being written and causing a click. Right? So if I have a 10-second buffer, then I'll be able to do 5 seconds of reverse delay, no problem. So I'm going to do almost all of it within Gen, but I will need to create a buffer to write to outside of Gen. So let's do that first. So buffer, just call it revdel for rev delay, and let's go ahead and do 10 seconds. That should give us plenty of space there. And now I'm going to want a waveform object just to track it. And what is it for? Would it be at object name? Or do I just need the waveform argument to be revdel? Let's see if that works. No, okay. Revdel. Okay, great. So, right, we see it's 10 seconds long, so we know it's referring to that buffer successfully. Now, okay, so let's do the very first thing, which would be writing continuously into the buffer. So for that, we're going to do that part in Gen. So let's make a Gen object, and we'll go in, and there it is in its standard form. I'm going to increase this to 125 so it's a little bit easier for folks to see. And we might need to go back to 100 as it gets more complicated, but for now it'll just be a little more visible. Okay, so first thing we want to do is to continually write to this buffer whatever the audio input is. So for that, we're going to need to poke into the buffer. So we, in order to refer to the buffer outside of the Gen object, we will need a buffer with the same name inside. And it's not buffer tilde because everything is audio inside Gen tilde. So we'll need a buffer with the same name, so revdel, and if we double click it, it should pop up with, yep, a 10-second buffer. So it's referring to the same buffer there. And the left outlet of this buffer will give you the length and samples of the buffer, which will be useful if we're going to be continuously recording over that, that exact length of buffer. So to poke and write to the buffer, we'll need a counter. We'll need the counter, although I believe this is default, we want the counter to count by 1, so that's the first inlet. The second inlet will reset the counter, and the third inlet is the counter limit, so it'll start looping when it reaches a limit. So we'll want the buffer length to be that. We're going to want the audio to come in here, and we're going to want the second inlet to be an on-off button. So for that, we'll use a toggle. And we'll want an equals operator to 0. And that will, so that means when it gets a 1, it will reset the buffer, or reset the counter, send the counter back to, send the counter back to 0. Okay, now let's test this. So we'll use our first outlet here as a tester, and we'll want to have a signal number box here. So now when I press this, we should see the counter counting up to the length and samples of the buffer. Oh, audio's not on. There we go. Great, so we see it counting up. It should count for 10 seconds, but then reach 480,000, I believe. Yeah, that's right. Because I'm working 48K sample rate. Okay, great. So the counter is working. So now in order to write to a buffer, we need to poke it. So we're going to poke and revdel, the name of the buffer. And we're going to want to, in the leftmost input, we want the value that we're writing. So that's our signal, that's our audio signal. And then we'll want the count writing the position, right? So the 0th position, first position, so on and so forth from the counter. So if it's in sync with sort of the looping of 0 to 480,000, it'll just wrap over and over and over, rewriting the buffer as it goes. So I believe this is all we need to be writing to the buffer. So let's open up some audio. I'll do a 2 piano piece of mine there. Play it in, and let's record it to the buffer. Oh wait. There we go. And it stops. And then it starts rewriting again from the 0th position. Great. All right, so we've got the writing of the buffer down. That's the easy part. Conceptually, what we're going to do with the reverse delay, we want to play the count backwards. So instead of going, so we'll peak the buffer, right? Peak is reading, poke is writing. So we'll peak the buffer, and instead of it going from, let's say, 10,000 to 20,000 in terms of the sample number, we'll go 20,000 to 10,000. So we just sort of run a counter backwards. And so we'll do that with a counter going to a scale object. But we want it to be have a few options. So I'd like it to be able to select an exact amount, exact delay time. So it's always 500 milliseconds or always 1,000 milliseconds. And I would also like it to be able to do a randomized delay time. So, and sort of set the limits of that. So the maximum will always be half the length of the buffer, but the minimum could be, 10 milliseconds. I mean, that might be a bit excessive, but it's probably, you get some interesting effects with the shorter delay times, depending on how you window it as well. You get sort of rhythmic effects. So, how do we want to start that? Let's start that by building sort of the easiest version of that, which would be the set delay time. We're going to want to have a parameter which we'll call delay time, and let's do at default. We'll do it in milliseconds, so at default will be 1000. And everything works in samples in Gen, so we'll need a ms2samps object. And so we should get 4,800 out of that, 48,000 out of that when we go there. Great, so that conversion is working. And then this should appear automatically here. So we got the adder object there, and it's at 1,000. So we can change that live here. Why don't we go ahead and test that? There we go. Great. Let's keep it at 1,000 for now, though. Okay. So we'll need to peak the revdel buffer. And we're gonna, the first sort of test will have tons of clicks in it, and we're gonna have to window it afterwards. But for now, we'll just do that. We're going to need another counter. Again, we'll want it to go one sample at a time. We can have it turned on by the same on-off switch. And then ms to sample, so this is going to be our maximum count, our count limit. And let's test that. So it should just count to 48,000, and it does. Great. So now we need to scale this. So it'll scale the input. So that's our input there. That's our, and then it's going to directly peak. Actually, let's test the scaling first, going there. So we'll need to set the scale, what we're scaling from and to. So, oops. So for now, we'll just do the 0th sample to the delay time, and then delay time to the 0th sample. So it's as simple as that. And then if we run it, yeah, see, now we're counting backwards. So let's get some audio going again. I'll turn it down here. All right, great. So we're writing in there. And so because of this, it'll always be sampling the first 1,000 milliseconds of the buffer. So that'll change as we keep building. All right, so we see that's working. We're gonna change this to out 2. It'll be our debugging outlet. Why isn't that? Oh, there we go. And we'll want a gain object on the first outlet and to send it also to the output here. And we want to, of course, send the scale object data to the peak object, and then that is going to go out 1. And let's see. There it is. So you hear there's a click at the beginning of an end. So that's something to get rid of through a windowing function. And then we're going to want to make it a little bit more dynamic than just always doing the first second of the buffer. Great, but you can see with this, there's a lot of possibilities from here in terms of sampling and playback within Gen. Okay. Right, so let's do the windowing function next. So we're going to want to, there's lots of different ways to do this. So I'm going to create a buffer that we're going to multiply our sample with. So I'll call it, let's call it win for window. And I'm going to do a nice even number of samples. Let's do 8,000 samples. And then I'm going to want another one of these. My win. Great. Right, and it's not showing the time there because 8,000 samples is quite short. Hopefully that's the reason why. We'll see in a second. So one thing that I know I'm going to need is an Uzi that shoots out 8,000 bits of data. I'm going to want it to start at 0. So it'll go from 0 to 999, so that I can write all the samples in quickly into the window there, into the buffer. So we're going to divide by 7999 and get the index of the Uzi. So this will quickly go from 0 to 1, and which is useful for the expressions or the algorithms that we're going to use to generate it. So first, let's choose a hand window. So for this, we're going to use a gen expression. So we're going to want out 1 to equal 0.5 minus 0.5 multiplied by the cosine of, 2 pi multiplied by the first inlet. Okay, and so as it goes from 0 to 1, we'll get the handing shape with that expression. And you could do similar things with like a hamming, or there's a bunch of different window types. But in order for this to work, we're going to need to poke the buffer. So we're going to poke the buffer named win. And so we'll want and it works very similar to the poke within gen here. So we want the the value to write in the left hand, and then the index, sample index in the second. So for the sample index, we just need to get the current index of the Uzi and put that into the gen, and I believe this should generate a Hanning window. All right, let's see if that worked. This is my problem here. At samps 8,000. All right, so that was, I guess, just one of my problems, and I must have another one here. Oh, I see the problem. It's sending out integers. I'm missing that. I just need that for the float, and that should do it. Yes, so there's my Hamming, or my Han window. And there's a way to make this display so it doesn't show the negative numbers. How do we do that again? Vertical zoom, vertical offset. Okay, so let's do 0.5. Oh yeah, there we go. 1, there we go. And we'll want a zoom of 0.5 so that actually shows the top. There, okay, so that looks like the window I want. So that's the Han. Is it Han or Hanning? Let's do Han. Okay, but I also want to just be able to decide sort of how fast the attack and decay are on my window as well, manually, like giving it sample values. So I'm gonna do a second here. Why don't I just encapsulate that? And let's do a second one here. So first I'm gonna wanna fill the buffer. So to do that, I could again use an Uzi 8,000, starting with the 0th index. And I'm just gonna poke it with a 1 for absolutely every place. So I'll just, the 1 in a message, it'll bang the 1 out each time. And we will poke window 1. It should be as simple as that, just to absolutely fill the buffer. There we go. There may even be sort of a fill operation that you can do directly and not have to bother with this, but in any case. So that'll be the first step of it. Now I'll want the attack slope and then the decay slope separately. And again, we'll use sine and cosine functions to create a curve. Let me close that up, get a little more space here. So we will need to have an Uzi, and the number of bangs it sends will be the variable that'll decide how many samples it covers. So I'll have a message here which will be attack time. We'll start with 4,000 samples. And I'll want an Uzi, and I'll have it by default at 1,000 samples, and I'll always want to go from the 0th sample. And then in the right input, how many times it bangs is there, so attack time will be there. And I'll bang it out manually for now, but we'll want to sort of chain it all together with a probably trigger bang 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 at the end to generate the window. But for now, we'll do it piece by piece. All right, so now we'll need to have an expression. So we'll need gen at expression. That way you just write it into the box rather than within the gen subpatcher. We want out1 to equal the sine of 0.5 times pi multiplied by the first inlet. So that should generate our attack curve. So let's see if that works. So I want the Uzi to bang. Oh, wait, hold on. No, I'm only using the index. So I need a division. Hold on, let me go down this way. So I'll need to divide it by 1,000 by default, but we'll put that in there as well. So it'll divide by the same amount, which is what we want. And we'll need the index to go into there, the gen to go to poke the window, and then the sample index from there. Let's see if that works. That did not work. Oh, again, I made the same mistake. I need floats. I need a little decimal point there. There we go. So I got my shape. And let's, whoops. Let's change this to be a little short. Let's do 2,000. There we go. So we see, you know, we'd have to rewrite it, then do that to get it all. So we'll chain that all together at the end, but let's do the same thing. So we'll use the exact same expression to generate the curve, but it'll need to be the cosine so that it's going down rather than up. Though I suppose you could do it with a sine with a different multiplier, but I'm not gonna think of that real time. So we'll just copy that all out. And I think if we change this to cosine, then that will work, though we'll also need to offset it. So we'll need the length of the buffer, which is 8,000, and then minus that amount. So that's all the same, but we'll need one extra thing here. So for this, it will be 8,000, so the length of this buffer minus how long you want the curve to be. So we'll need an addition here. And actually, it should be an integer because we're just getting samples and we're not interpolating between samples. So we'll need an addition here, and we'll need this number minus, oh no, we'll need 8,000 minus that number. So I believe we do that with subtraction with the inlets reserved. Yeah, reversed. 8,000. All right, let's see if that works. And this will go into here, and then that ought to do it. Yeah, perfect. Okay, so we're gonna need to have this all happen at once. Let's get rid of our individual bangs. So we want trigger, actually we want 5 if we're going to be doing it like this. Trigger bang, 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 bang. So first we'll want to fill the window. Then we'll want to get the, actually here, we don't need, we can just do it in 4. So first we'll need to fill the window, fill the buffer. Then we'll need our attack and decay times. And then we will need, oh, I only need 3. Oh, I have to rewrite it every time, that's annoying. Okay. Fill the buffer, get our times, and then poke it. Let's see if that works. I wonder if doing the poke separately is better. Let's see. So first I'll just, hold on. I need to make sure it works by doing this. All right, great. So now if we change, hold on. Let's change these to test it out. Let's do even shorter. Let's do 1,000 samples on each end. There we go, great. So we could probably do this all in gen, but the buffers in gen will refer to buffers outside of gen. So anyway, this is a perfectly good way to do it as well. Let's clean things up a little bit. Okay, great. So hand window, just do custom window, attack, and well, I've been saying attack and decay, but it's really attack and release. Sort of. Great. So, but in any case, for now, we'll do the hand window. Nice, smooth. Actually, let's do our harsh window. Okay. Great, so now we can head back into gen and do the windowing. So we'll need to synchronize this counter, I believe. Yeah, we'll need to synchronize this counter with the 8,000 sample peak of the window 1, which we will then multiply with our peak from the rev delay. So we'll definitely need a multiplication object here. And we will need to peak the window 1, and we'll be multiplying those. Okay, great. And we want it to always go between 0 and 8,000. So we'll have to use a multiplier to do that, or rather divide the amount to get it to fit. And because of this, we're also going to be not reading just integer sample values, but we might try to call sample 1.5. And for that, in gen, we can interpolate. So we want at interpolation, and there's different types of interpolation: linear, cubic, and cosine, and spline. I'm not sure what spline is, but in any case, in my experience, cubic has sounded the best. I'm not sure, so we'll do that, and we'll also. Oh, that's all we need for that one. Failed to compile patcher. I'm not sure why that is. We'll figure that out later. Just in case, let's put an interpolation to cubic on this one as well. At bound mode wrap. So that means if I try to call a sample that's outside of the window, it will sort of flip back onto it at the other end. It'll wrap around. I'm not sure why I'm getting those. We'll see. Oh, window 1 is not defined. Right, I need the buffer within there, within the gen patcher. So buffer window 1. So now that issue should be gone. Okay, and we'll need that for the length and samples anyhow. So I'm going to want to synchronize this buffer with the count. So for that, I'm going to use a division. So I need to do 2 divisions. All right. The second one is going to be this one. So I want the counter, and I want the total size of the count. So for now, it's just going to be this delay time. So first I'm going to use it, divide by the delay time, and then divide it by the counter. And then let's check our work here by sending it to our debugging thing there, and then turn it on. So it should be continuously counting down. Yeah, great, from 8,000 to 0. So with that, we just peak our window and then multiply it, and then we have it. And and it should be in line. Yeah, okay, let's listen to it and see if it works. Right, and we can hear how the different windows sound different. Harder attack. And you heard that we got a click there as it was rewriting the first second, because once again, we're only applying this to the first second so far. Great. Okay, so we have the reverse delay is now being windowed successfully. And we can move on to brighter pastures. So there are 2 more things I want to do. One is randomize the length of the delay time. And the other is I want it to begin the delay from the point of the buffer that is currently being written. So it'll reverse sort of from the most recent moment and play backwards. So the sample that is being written is available in the count here. So we're going to use that, and we're going to sample and hold that, because we'll want to give the we'll want to add that number to the starting place of where we peak the R delay. But we'll want to do it just once at the moment. We'll want to sample that number at the moment where it begins reading. We'll use the flag from the other counter to decide when it's being sampled. So to get that flag, we will do equals 1. Grab the flag. Will this work with the? Let's see if it works with the flag. Yeah, good. Okay, it works better with the flag. Great. And so then all we'll need to do there is add that number. Oh, actually, it's not quite that simple, is it? We will need to add a number here after the scale object. All right, so we'll need to do an addition there. And we will need to take away the delay time, right? Because okay, let's see if that works. All right, to debug it, we'll take this. Great, so it seems to be following as it goes, and we're hearing no clicks. Beautiful. So we have basically a fully functional reverse delay where we have a set delay time at this point. So we can lengthen it. Let's try really short. Yeah, it's kind of a cool. And if we change the, you really hear the difference there of the window. 500. Great. Right now we have the first inlet, the audio is being sent in, and it's giving the value to write to the reverse delay buffer. And a counter is being turned on and off with the toggle, telling it which index to write into this buffer. And we have the length of the buffer being the count limit for the counter, so that it's continuously writing, wrapping around and writing that buffer. And then at the same time, we have a counter that is playing back from the same buffer, but instead of going forwards, it's being reversed using the scale object. So we have 0 to the delay time, scaled delay time to 0. And that's being controlled by the delay time parameter here, which is being converted from milliseconds to samples, because it's much easier to think in milliseconds, I find. The counter flag, so every time the counter hits a 0, it's sending a signal to the sample and hold to sample the current place where the rev-del buffer is being written to, and it adds that amount minus the delay time to the scale. And that's because of how the scale is working. So if we were going, we could actually avoid that step if we went from 0 to the delay time, and then 0 to the negative delay time, right? By shifting it there, but instead we're shifting it here. And so that's being added to the scale so that it follows where to play back the reversed sample, which is being done through the peak object here, referring to the reverse delay again, which is being windowed by the buffer that we created, which is 8,000 samples long. So we're taking that length of 8,000 and we're using it, we're dividing the delay time by it, and then dividing that, dividing that with the current count and peeking into the window so that these two, what we're playing back from the reverse delay is being synchronized through this counter with the 8,000 samples in window 1. And we're using the interpolation function because, of course, we'll often be calling back tens of thousands of samples from this first buffer, where we only have 8,000 samples here. And so we're relying on this interpolation function to call back, sample 1.2, 1.4, 1.7736, or whatever. And then we're multiplying those signals together, and that's the windowing and sending it out. Okay, so the last step I want to take is to have a randomized delay time. So this could be done outside of Gen, probably more easily than within Gen. If we're just sort of, we could have an outlet that is taking the carry count here, and we're changing the delay time every time. Maybe you have random 5,000, and then it'll be anywhere between 0 and 5,000 milliseconds every time. But we're going to do it within gen because it's kind of more challenging, interesting, likely more efficient as well. Almost certainly more synchronized with, or it'll be synchronized at the sample rate with the flags that being sent by the counter as well. Okay, so we're going to need a little space for this. So to do this, we're going to use noise to generate random values. I'm going to go ahead and get a couple of debugging outlets here prepared. So noise is going to generate numbers between -1 and 1 continuously at the sample rate. So every sample is generating a random number. So we're gonna want to constrain that a little bit. So we could do +1 and be 0 and 2, but instead I'm just going to do an absolute value. So it'll always be between 0 and 1. There we go. So then we're going to want to multiply that by our maximum size. And in order to avoid clicks, we'll want that to be, the maximum size will be half the length of the revdel buffer. So we'll just need to have a multiplier there. And then we'll need to take, we'll divide it by 2. Multiply by 0.5, divide by 2. Same difference, and we'll get the length of revdel there. And we will multiply it. And let's see what we get there. So it should have, well, it's hard to read as samples, so I'm going to get rid of this after, but we'll do samps to milliseconds. And it should max out at 5,000. So yeah, we're seeing no values above 5,000 there. So we'll have our value here. And so we're going to want to be able to switch. We're going to need a second toggle to switch between a static delay time and a randomized delay time. So let's go ahead and add a third inlet. And we're going to want it to be just like this one. That turns the main thing on and off. And we're going to want to hook it up to a switch so that we can choose between two inlets. So I'm going to double check which one's which here. So for that, I will just send, let's put the delay time in the first inlet and the randomized delay time in the second inlet. And send that to out 2 and see what we get. Okay, so that's the static one. Oh, I'm gonna need another toggle. Right, so when it's on, it gives you random. So let's add a couple comments to this here. So we're going to need to get rid of all 3 of these and instead have the switch going to them. So I'm going to do that first so I can keep track more easily. So this goes to the 2 middle ones. And then the last one is there. Get rid of the original ones. Am I missing one? Oh yeah, the counter. So it's 1, 2, 3, 4, 5. Okay, great. Get rid of all those. It's up here. And that in fact may do it. Let's see if it's working. So again, play some piano in, start it going. All right, something's off. All right, so we'll need to figure out what that is. Ah, we need to sample and hold that value. Of course. We'll use a latch. All right, so input to sample allows input when non-zero. All right, so how do we want to do this? So we'll want a new value every time that it every time that the counter flags that it was returning to 0. Now this might cause a feed, we might need a history object. So in fact, let's put this into the switch and let's see if it still lets us attack. Yeah, okay, so we're gonna need to use the history object, which delays by 1 sample, and it allows for feedback loops. So our count, and then to the latch, and let's see if that solved our problem. Okay, interesting. Let's go over the steps one last time. Okay, now it's fully working. Okay, so for the reverse delay, we have our buffer object that we're writing to. We're poking using the counter and the signal input to write this buffer continuously. And if we change the length of the buffer, this will change dynamically as well because we have the buffer length within the gen patch. 50% or half the size of the buffer is the maximum reverse delay time, or else you're going to be referring to parts of the buffer that are being written and you'll get a click at that moment. Some people that doesn't bother, but for whatever reason, clicks really bother me. They sound like errors somehow to me. In any case, so we have that portion writing. We have the window function that we generated here in a second buffer where we can customize the window or just use a hand window. Hand windows are ideal for overlapping and creating the sort of the sense of continuous sound. We'll use this custom window though, I think as sort of a standalone single delay line. It sounds better when it's windowed like that. If you were to sort of combine 2 or more of these, the hand window could be more interesting texturally, depending on what you want. It really does sound different. Then we are sampling back the reverse delay buffer by scaling a second counter from 0 to whatever the delay time is and back. And then we're adding a number that corresponds to where the buffer is being written, so that it's always playing the reverse sample from the current moment rather than always like the first second of the buffer. And we are also having a random option, so you can choose with a second toggle here represented by inlet 3 a random number which of which the maximum is half the length of samples of the reverse delay. So again, because of that click issue, if it's larger than that, we're putting that into a latch, which we are triggering with every sort of new sort of cycle of the window. And the switch is being used to choose between the static delay time and the randomized delay time. And then we're multiplying that output with the window, which is scaled using these 2 division objects to avoid clicks at the start and end of the reverse sample. And that's the whole thing. So maybe I'll just play some guitar with it for a little bit. So I got my guitar in ADC3 there. So let me stop this. Let me, instead of the input being from my SF play, use ADC. And let's see how my guitar is sounding. All right, I need to. There we go. It might be a little noisy. Yeah, so we got a little bit of noise there. Oops. All right. Oh, the guitar is a little bit below the screen there, but there it is. Great. So let's just try it out.